lot. Thanks for the organizers for organizing this conference and giving me the opportunity to speak in front of such a distinguished audience. So most of the people I'm going to cite are actually present. I mean, not most, but more than half probably. Also, you notice that I'm not Ramila. I noticed this too. Yeah. Okay, so I'll tell you what the motivation is, the main motivation. The motivation is, what do SLN homologies say about the smooth concordance class of a knot? Okay, so I'm afraid that I'll probably, with this motivation, I'll already have lost half the audience, because there are many people maybe interested in SLN homologies, because they come from quantum SLN, from the representation theory. And then there are maybe some people who are interested in topology, but so if you're just on either side, then well, try to get that side from the talk. So because of that, I think I'm actually going to define very quickly what smooth concordance is. So we consider knots with the operation of connect sum, which makes knots into a commutative monoid. And then, well, because a commutative monoid is not so interesting as a class, and also because of other topological reasons, we quotient out by an equivalence relation called concordance. And concordance means that K0 is concordant to K1 if there exists a smooth cylinder, so a smooth embedding of the cylinder into S3 cross I with well, the image of C intersected with S3 cross I is Ki. You think of this like a map from one knot to the other. And then to be correct, I should maybe write minus 1 to the I here, which means one of the knots is mirrored with orientation reversed. I should also suppose that this map is proper. Okay, so that's one of the main actors, and the other are SLN homologies. So there are very many different flavors and variations, and what I'm going to consider is the following. We have, for each monic polynomial of degree n, we have one homology theory. So for me, SLN homologies, or at least in this talk, are for each monic P in the complex with complex coefficients of degree n. We have a machinery which associates to a knot diagram a filtered complex, chain complex, which I call CP of free Cx divided by P modules. Okay. So if I have enough time, then my talk will have 4 parts. In the first part, I'll talk about the classical stuff you can do. So this is resonance invariance. So classical, I have learned now, means that it was done before the things that I'm mainly going to talk about. So it's classical in that sense. And then I'm going to talk about the new invariant, which is not yet classical, which the title indicates, which we call GIML. And, well, then we'll see some topological applications. And finally, we are going to consider a picture which unifies these homologies a bit, and we're going to talk about equivariant homology and what concordance invariance you can get from equivariant homology. So, yeah, let me start with part 1. Resonance invariance. So I'll actually try to define this complex CP. Let's see how that goes. So to this crossing, I will associate a short chain complex, length 2, namely this one. So this is a chain complex in which the objects are Moy graphs, trivalent graphs in the plane with some additional structure. And the maps, well, for aesthetic reasons, I will say they are foams, although I actually don't much care in this talk, but I can draw foams. So I think you've seen this picture before. I mean, before in this conference. So that's like a special kind of CW complex, something that locally looks either like a surface, either like the plane, or like the letter y times an interval. And then, well, this is of course not going to be very exact, so there are some degree shifts, which I'm not writing down. So now if I have a whole knot diagram D, then I can get the diagram D by gluing together such parts. And then I use some algebraic machinery, which you can call, I don't know, 2 categories or canopies. I don't really care much, just do the sensible thing, which is you glue together. This corresponds to tensoring of the complex. So in this way, you get here a graded complex of Moy graphs and foams. So here the Moy graphs were allowed to have open ends, and here everything will be closed. So this picture here explains what happens in this step. And the second step is to associate to this something really algebraic. So to associate to this, well, the announced filtered complex CPD. And to do this, you have to evaluate the graphs. The graphs will give modules, and the foams will give maps. So as probably many of you know, that's rather a complicated process. Somehow it's clear how to evaluate the graphs. I mean, nowadays it's clear. But evaluating the foams is less obvious. But I don't really want to talk about this. It appears that there's only one sensible thing to do. that's a very vague statement, but so there are lots of different ways to do it, but so far it appears that they all give one thing, which somehow hints at the fact that there's, well, only one good thing you can do. And so here you need to evaluate forms. And I mean, this category of Moy graphs and forms contains a category which is much simpler as a subcategory, namely those of just one manifold in the plane and cobordisms between them. So an evaluation of forms includes in particular an evaluation of that subcategory, and something like that is called the TQFT. And apparently, well, you have a choice for the TQFT, but apparently choosing the TQFT then determines the whole evaluation of the forms. So this is apparently determined by a choice of an evaluation of surfaces, and such an evaluative procedure is called a TQFT, and our TQFT is going to come from a Frobenius algebra. And, well, this Frobenius algebra is where the polynomial comes in. It's the Frobenius algebra Cx divided by P. So that's your definition of SLN Khovanov-Rozansky homologies. Now you can sit down and calculate. That's not quite true, but so what we have is this family parameterized by a polynomial, and well, one of the first questions would be which polynomials give the same homology theories in the end. And we have one thing we can say about this. We have the following isomorphism of Frobenius algebras. Cx divided by Px is filtered isomorphic to Cx divided by Pax plus b. And because I want it to be monic, I have to divide again by 1 over n. I call this Qx. These two are filtered isomorphic, and this induces an isomorphism of the corresponding chain complexes. And now, when you think about this geometrically, I mean, a polynomial is given by its sets of roots with multiples. So you imagine the polynomial p being given by its roots in the plane. Then what this does is you're allowed to shift the roots, rotate them, and stretch them. So if you have only two roots, then modulo this relation, you will end up with only one of two possible isomorphism types. Either you have a double root, or you have two single roots, but all those choices are the same via this relation. So for n equals 2, any Cp is isomorphic to either Cx squared or Cx squared minus 1. So to Khovanov homology or to Lie homology. And now it turns out that this choice gives you concordance information. So, I mean, all these complexes are up to homotopy equivalence, not invariants. So these are, I didn't write it down, but these are invariants up to homotopy equivalence. But of course, they need not be invariant under the concordance relation. It turns out that for this choice of polynomial, it is. So h cx squared minus 1 of the diagram has a very simple form. So since it's a graded homology, I'll write the dimension as a polynomial where in two variables, in t and in q, where t corresponds to the homological degree and q corresponds to the filtration degree, so the quantum filtration. So this has the form q to the s, I write it as s2k times quantum 2. And this is the Rasmussen invariant, which is not just a concordance invariant, but actually a homomorphism from the concordance group to the integers. So now, in view of the motivation, the first question we can ask is this everything we get in the case SL2 for Khovanov homology? And I guess that's an open question. So I guess the conjecture would be yes, this is everything we get, at least if we work over the complex numbers. But it's not very clear. Admittedly, it's also a vague question. Okay, so for n equals 3, bigger or equal than 3, the situation is a bit more complicated. You still have this relation, but now if you think of 3 roots in the plane, this relation alone is not going to give you finitely many isomorphism classes. Simply because you have 3 coefficients, and this allows you to kill 2, so you'll have at least an infinite 1-parameter family left. And what is still true is that if we pick any polynomial with distinct roots, we will get a concordance invariant. So p without multiple roots implies that h of Cp is the concordance invariant, but it's not necessarily a homomorphism anymore. Or let's say it's not necessarily encoded in such a way by a homomorphism anymore. So, for example, let's take Cx to the n minus 1. This will give something which is still a homomorphism. And, well, we'll call this a generalized Rasmussen invariant, denoted by Sn. And here it will just be quantum n. But, well, to give a bit more concrete examples, for example, for Cx to the 3 minus x, this will not be a concordance homomorphism anymore. So that means, in particular, it will be 3-dimensional, but the filtration degrees of the 3 generators can do anything. They don't need to be nicely stacked as here. They can be all over the place. And we don't actually know how many different invariants you get. So when we started to look at this, it turned out that it's more chaos than order. So for example, this x to the 3 minus x minus 1, and well, let's say this, are all different invariants. Okay, so while for n equals 2 we have kind of a candidate for the answer of the motivational question, namely that there's only this one concordance invariant. Starting from n equals 3, it seems to be really chaos. We can say some things, but we don't have one structural theorem saying these are the different invariants and nothing more. Okay. So next I want to tell you about, yet another way to get concordance information from SLN homologies. So for this, we take a different kind of polynomial. We take p equal to x to the n minus x to the n minus 1. So far, all the concordance invariants we know come from a polynomial with distinct roots. And now we are going to see how to get something from a polynomial which has a, in this case, one single root and one n minus 1-fold root. And now you see that modulo this relation, it's the only polynomial with n minus 1-fold root and a single root. So the choice of this polynomial is less arbitrary than it may seem. So this is modulo star the only polynomial with a single and a n minus 1-fold root. Now we have a decomposition theorem. We know that the homology of CP is isomorphic to the homology of, well, what we can do is we can factor this polynomial, and then if we have two factors which are coprime, then that splits. So this means we have an isomorphism to the homology of C x to the n minus 1 plus C of x minus 1. That's a theorem was proved by Rose and Wedrich. So you see that this applied here, if we take a polynomial without multiple roots, immediately gives us that h of Cp of such a polynomial splits as n copies of an h of C of a linear polynomial. And the linear polynomial will give you SL1 homology. And now, as you might know better than I, SL1 homology is always trivial. It's always one-dimensional for whatever knot. So you could think that this theorem tells you that the only interesting homologies are basically x to the n for varying n, because you get all the other ones as sums of these. But the crucial thing is that this isomorphism does not preserve the filtration. This is not filtration preserving. And the general idea is that any SL1 copy gives you something which is a concordance invariant. So here we have this SL1 copy. So this is one-dimensional. So let's pick a generator. And this decomposition is actually makes some sense. So this is this one-dimensional space is the eigenspace This is the one eigenspace of multiplication by x. And so you know that psi, and so you actually see how that space looks like. It's x to the n minus 1 times Cp. So remember that we have an action of the Frobenius algebra. I didn't tell you how, but it's via a base point. So we can identify this summand as, well, all elements in Cp which are x to the n minus 1 something else. And now you see if we multiply with x again, because the polynomial is this, and we divide by the polynomial, nothing will change. So that's the one eigenspace. So we should get a concordance invariant from psi. And there are two ways you could accomplish this. There are two ideas. So of course, what you must do is what we always do. You take the filtration degree. You take the quantum filtration degree of this element psi. But you have, that's somehow an ambiguous statement. You have a choice in which space you take this filtration degree. So the first idea is idea 0. You take the filtration degree of psi in that eigenspace. So take the quantum filtration degree of psi in H in the homology of x to the n minus 1 Cp. So this is what corresponds to the summand. So this is a one-dimensional space generated by the class of psi, and you have quantum filtration degree in there. That's the first idea. And it turns out that this will indeed give a concordance invariant and even a homomorphism. Gives a homomorphism, concordance homomorphism. But there's a different way you could also do it. Psi also lives in the whole space. So you could just as well, I mean, psi is uniquely identified up to scalar multiplication. So you could just as well take the quantum filtration degree of psi in HCP. Now, if you think about how a filtration of a complex induces the filtration on homology, so the way it does that is you take the element in homology which is cohomologous to your fixed element of the best degree. So you have a bigger space here. So this could give something of a better quantum degree. And it turns out that it does sometimes. So these two need not be the same, but this also gives a concordance invariant, but not a homomorphism. And well, there's no clear way to say that one idea is better than the other. For some topological applications, you want to have a concordance homomorphism. For example, for detecting summands in some quotients or subgroups of concordance. For other applications, you do not want a concordance homomorphism. For example, for detecting torsion. And also, if the two invariants are different, then always one can be better or the other. It's impossible that one is always better than the other. And so we take the third option. We take idea 0, 1, which is we interpolate between the two. And we do this similar to, as the title promises, we do this in a way similar. The Upsilon-invariant was constructed from Heegaard-Floer theory. So if you don't know anything about the Upsilon-invariant, well, you see how it goes. As ingredients, we need two filtrations. So we have one already on our complex, which is the quantum filtration. But it turns out we have a second one. So there's a second filtration. And this is given by the action of the Frobenius algebra. It's given by the multiplication with x. So it's simply 0 is contained in x to the n minus 1. Cp is contained in x to the n minus 2 Cp, and so on until xp Cp, until Cp. And if you look close, you'll see that this filtration is respected by the differential because of the complex, because the differential of the complex, the complex is a complex of modules over the Frobenius algebra. So the differential commutes with a multiplication by x. And, well, if you multiply by x, you only rise in this filtration. And then because of the particular choice of potential, x to the n minus x to n minus 1, if you are here, you don't go back or something, you're just stuck here. So this is a second filtration, which is respected by the filtration. And now the idea is, if you have two filtrations, you can mingle them together, and you can take a different dosage. You can take a high dosage of one and a low of the other, or the other way around. So you get a one-parameter family of filtrations. So this gives a one-parameter family of filtrations. I call them GT, and I don't think I'm going to write down the formula. It's not so enlightening. The idea is that for t equals 0, it's equal to this filtration. For t equals 1, it's equal to the quantum filtration. In between, you interpolate. And now we define Gimmel n of t of our given knot as the GT filtration degree of psi. And there are some normalizations. So I'll tell you about some of the properties of this invariant. Maybe I'll give an example first. So for the trefoil, we expect this to be boring, and it turns out boring means well, I mean, what is this? This is a function from 0, 1 to r. And boring means linear. And indeed, for the trefoil, the function is just this. And here it depends a bit on normalization. Let's say it's 1. But then, for example, for the 7 minus 3 pretzel knot, which I will draw later on, we get something non-linear. We get this function, which goes to minus 5/8 at 1/2, and then to minus 3/2 here. Yeah, you're right. The example I'm giving is actually, in this case, Gimel 3. Yes, and it may change with n. Well, for the trapole, it's always this.
So for positive knots, it's always linear?
Yes. Yes. So, well, since you ask, I'm going to, well, let's say, so it's piecewise linear. And then this is a typical phenomenon that for these concordance invariants, we have classes of knots for which they are in some way boring. For example, for the Rasmussen invariant or the Heegaard-Floer tau invariant, boring would mean equal to the signature. And here, boring would mean, well, just linear and giving back at 1 an invariant we already know. So I'll give you the class for which this is boring, i.e. linear.
But if except you get a bound on the number of breaks, if n is fixed, say n equals to 3, is there a
Upper bound on the number of breaks?
yeah,
Well, I don't think so, no. So I can't reply with absolute certainty because we haven't computed enough examples, but my guess would be that the number of breakpoints depends rather on the complexity of the... well, wait. I wanted to say on the complexity of the knot. Yeah, that's my guess, but I'm not absolutely sure. All right, so it's linear for example, positive knots, but even more generally, quasi-positive knots. And then alternating knots, or even more generally, homogeneous knots, if you know what that means. Otherwise, just pretend I wrote alternating. But interestingly, it is not necessarily linear for quasi-alternating knots. I'm not going to define quasi-alternating either, but it's quasi-alternating knots are what, for example, Khovanov homology and not Floer homology are in some sense boring. But these are not. In particular, this knot is quasi-alternating. So there is a heuristic reason for that. I already wiped out the defining definition, but if you recall the defining definition, the orientation plays a role. Whereas in Khovanov homology, the orientation only comes in at the end by a shift, but the relationship is inherently unoriented. And the heuristic is that quasi-alternating is, in a way, also something defined via an unoriented relation. So it's not so surprising that these invariants, which in a way pay more attention to orientation, need not be boring for or standard for quasi-alternating knots, while Khovanov and Floer need to be. So the general idea is that the information we get here from SLN and the information we get from Floer and Khovanov are really orthogonal. All right. Let me tell you some more properties. So the idea was to interpolate between these two ideas, and that's actually what happens. So if we take the derivative, the right-handed derivative at 0, we get what was defined in idea 0. And if we take the value at 1, we get the invariant defined in idea 1. And well, it's a concordance invariant. And it gives a lower bound to the slice genus. And then, well, the fact that this is a concordance homomorphism and that isn't is reflected in the fact that this function is additive with respect to the connected sum near 0, but away from 0 it's not necessarily additive, but it's at least super additive. So it's additive with respect to the connected sum near 0 and super additive everywhere. So if you know upsilon, then you see some similarities, but for example, upsilon is additive everywhere.
How does it behave under mirror?
Strangely, we don't really. I mean, you can cook up some inequalities, because if you take the mirror image, you add the mirror image with orientation reversed to the knot, you get a slice knot. So you know that Gimel is trivial for a slice knot, and then you know it's super additive, so you will get some inequalities, but we can't say anything beyond beyond that. And actually, we'll see a strange example of behavior under mirror.
Do you by any chance see any flat lines for like a negative opposite?
So we are only working for knots.
Oh, yes.
I guess you could do it for links, but and well, also a Hopf link would be torus link in particular positive, so nothing interesting happens for positive knots. But yeah, we'll see an example in a minute where the mirror image looks quite different from has quite different Gimel than the knot. Okay. Right. So let's look at some geometrical applications, topological applications. So I want to introduce a property of knots. I want to call a knot squeezed. If there is a smooth cobordism between a positive and a negative knot of optimal genus, which factors through the knot. So if and only if an optimal or minimal genus smooth cobordism between a positive and a negative knot factors through K. Let me give you an example. If we take, let's take the figure 8 knot. So now is a bit the point where I out myself as a topologist. So from a figure 8 knot, for example, you can find a cobordism of genus 1 which goes to this knot, which has these two crossings switched. And I'll give you some seconds to figure out what that knot is. You can also take like mirror image of that cobordism to switch the other two crossings, which will give you a genus 2 cobordism from this knot to this knot, which factors through the figure 8 knot. And now I hope you figured out that this is the positive trefoil, so in particular a positive knot, although it's not a positive diagram. This is the negative trefoil, and it's simple to show that genus 2 is the best you can do between the positive and the negative trefoil, so this knot is squeezed. So I don't know about your intuition, but if you see this definition for the first time, it might seem a bit outlandish to you. So you might have the impression that this is a rare property, but actually the contrary is true. Quasi-positive knots are squeezed, homogeneous knots are squeezed. So you might start to guess where I'm getting with this. And you can show this by drawing nice pictures similar to this. So where I'm getting at is Gimel is linear for squeezed knots. So one topological application you have is you can obstruct squeezedness, which is actually not so easy to obstruct. The only obstructions I know come from Khovanov-Rozansky homologies. Or Heegaard. I mean, you could also use tau from Heegaard-Floer homology, but the only obstructions I know come from categorified, these categorified concordance invariants. So, in particular, this knot is not squeezed. But, for example, if we change the signs, we get a squeezed knot. So P minus 732 is squeezed. And I'll show you how. So I'll draw this knot. This is 7 crossings. Then 3. And then 2. This is the minus 732 pretzel knot. And you have a genus 3 cobordism, where you change these 3 crossings, which goes to the P minus 7 minus 3 2 knot, which is negative. So don't let the sign at the 2 fool you. That's actually a negative knot. And you can take a genus 2 cobordism, which I will not reveal, to the unknot. And the unknot is in particular positive. So there you have an optimal genus smooth cobordism between a positive and a negative knot. This is actual optimal genus because this has genus 5. So this knot is squeezed. And I'll show you another application. also with pretzel knots. For example, I claim that this pretzel knot minus 7, 6 summed with the mirror image of 7, minus 5, 4, this knot, is it's not just not squeezed, but it's of infinite order in the concordance group divided by squeezed knots. So I don't know if this excites you particularly to know that this quotient has an element of infinite order. But the point is a bit, it's a topological application, and I don't really know which other invariant you could use to produce this result. Because, for example, for this knot, I mean, it looks a bit arbitrary, but the reason it's chosen in such a way that all homomorphisms, I know, all concordance homomorphisms from Khovanov-Rozansky and not Floer, they are all 0. All the homomorphisms are 0. Tau is 0. Upsilon is 0. And the S2, S3, and so on, they are all 0. And the proof is not so hard. So I call this knot K. Gimel 3 of K is nonlinear. It has also one breakpoint. But, and here's your example, the mirror image of K is linear. So now suppose this knot K were of a finite order in this quotient. Yes. Thank you. Otherwise, that would not be a good result for mathematics. Yes. So suppose some connected multiple of the knot is squeezed, which would mean that it is of finite order in this quotient. Then Gimel of that knot were linear. But then I can write, then I get that K is concordant to K to this knot, added with, well, I add K to the minus 1 copies of minus K. This is just because a knot and its mirror image with orientation reversed are inverses in the concordance group. And if you look at this sum, all of the summands have linear Gimel. And then we have a little lemma that although we can't generally very well control the sum of Gimels, if we add linear Gimels, we stay linear. So we have a contradiction. So adding linear Gimels gives a linear Gimel. That's a contradiction. So this lemma is not so hard to deduce from the properties I gave. Well, maybe maybe you need some more properties, but it's not so hard to deduce from that. But I lack a bit the time. Okay. Let me think if there's something I can say about equivariant homology in 2 minutes. I think I'll just try. So that was your topological application. And now comes equivariant homology. So the idea is that instead of taking just a big swarm of independent chain complexes parametrized by a polynomial, we can actually treat the coefficients of that polynomial as formal variables, and we get one chain complex which unifies all the information of those. So taking the coefficients of P A0 plus A1x plus x to the n as formal variables leads to a chain complex of 3 modules, and there are C80 A1 an to the n minus 1x divided by P modules. And then you can imagine that the idea is that if you evaluate, so if you replace these formal variables by some complex numbers, then you actually get that complex here back. So that exists. I mean, that's highly non-trivial that this exists as a result by Krasner. And the idea is now that you would hope that just as the SLN homologies are unified by this, it's also possible to unify all the different concordance information from SLN homology in one thing, although it's not so clear what that thing should be. And, well, I'll just give you the result. I call this chain complex CEQN. So CEQN has a summand which is well defined up to isomorphism and is a concordance invariant, which is a concordance invariant well defined up to, well, you would expect chain homotopy equivalence, but it's actually isomorphism. And this summand contains all the information I previously wrote on the board. It contains the S2, S3, it contains Gimel, but somehow in a bit less readable form. I mean, here, for example, you have these properties, so it's easier to use than, well, this summand. But this could be the answer to the original motivation. This could be all the concordance information you get from SLN homologies. Thank you.
Questions? Upsilon in linear first please not.
Sorry?
Is the Upsilon linear
Yes.
first please?
I think I actually didn't. No, I didn't write it, but is Upsilon? No. So, for example, Upsilon is not even linear for torus knots. So, we have a lot of formal similarities to Upsilon, but the knots for which the invariants give interesting results are quite different. Yeah. So I think Upsilon is linear for quasi-alternating knots, but there again, Gimel is not linear. So there you go. Is it? Should I? Or
just out of curiosity, so do the you said the linear guys were homogeneous. Well, so homogeneous knots are linear with respect to Gimel, right?
What kind of knots?
You said homogeneous knots are linear.
Yes, that's
They
right.
also act in an additive fashion on. So does connect summing with them act additively on Gimel for?
Yeah, that's true. So, so it's not true in general that adding with a linear Gimel just acts additively. That's not in general true. But it turns out that for squeezed knots, and in particular for homogeneous knots, this summand is just one-dimensional and has no differentials. And so if you take the connect sum, it corresponds to taking the tensor product here. This will just result in a shift of all the invariants. So yeah, that's true.
In the interest of time, we might save further questions till the next break. And we will start when Ben is ready, in a couple of minutes.